So we're looking at how do we take a more complicated circuit and break it down into a simple one. And I want to make sure we're all on the same page here. So we'll start actually kind of manipulating the ones you were looking at yesterday. So you've got your series and your parallel stuff. I don't like that little. Do that? Oh, yeah, go like that. So I don't. What I'm going to do, if I could learn how to speak, so notice the current is different in each one of these spots. Hopefully you're able to do okay on the quiz yesterday. I really like how you can see the flow of electrons. One of the things they ask you to do is on C, on the little worksheet thing, on C it says, imagine you and your friends are running through the neighborhood like electrons. Well, this person has a pretty easy path, so they're able to make it around a bunch. Like this is maybe your house. And then this is one street, and then everybody's got to go across a cross street. Well, this cross street is like really easy, and this one has some hurdles, and this one has like a wall you've got to go over. But these are like the common streets that everybody runs on, right? So you go down one block, run across an easy street, and come back. And your buddy goes down 2 blocks, and he goes across this harder street and then comes back. But you see, you've got this higher current here, right? So houses are put together like this. So when you're plugging things in, what you notice is the more things you have plugged in, the more current you have in some certain spots in your house. So this is where you put your circuit breakers and that kind of stuff. So if I want to build one equivalent resistor, right? Because what we're going to start moving towards today, towards the end of the day, is let's take a more complicated circuit and break it down into a simpler circuit. And you might have some series and some parallel. So I'll need to be able to do an equivalent resistor. So if you look, this is not the equivalent resistance to this, right? So in series, it's pretty straightforward. You just add up the 3 resistors. So you probably saw in series where the equivalent resistance was 16 ohms. So you just took 10 plus 5 plus 1, and that was your equivalent in series, right? So in series, you add up each resistor, and that's your total resistance. So it's like you went across the easy street and then across the hurdles and then across the wall. So it drops your current very, very quickly. With this one, it's not as obvious. What you do is you add the inverses. So I'm going to add 1 plus 1/5 plus 1/10, and that gives us 1.3. And then I do the inverse of 1.3. And so my equivalent resistance is 0.769, right? So if I double click on this thing and I think I can get to, well, you can't do 0.769, but I can, 0.5 catches it on fire. See, I should have tried this first. So I can't do an exact 0.769 on here, but if you look, this is pretty close now. 9 amps. Oh, well, yeah, because that's the 1 amp. It's going through like it's 1 amp. But if I lower it down now to 0.5, because I can't go to exactly 0.7. 0.7 should give us the total current of 11, right? But if I drop this to 0.5, my current is 18. So you see, like it's getting closer. If we could do 0.7 here, you'd get that exact thing, right? It's on fire a little bit. I guess I should raise the resistance so it doesn't go quite as fast, right? So you can make an equivalent resistor, right? So in series, I add up the resistances, and that works. In parallel, I add up the inverses of the resistance, and then I inverse that, right? So we've done that a couple of times now. We're going to jump to the board and look at some slightly more complicated ones now. All right, so we take a look at a little bit more complicated circuit, and we'll get a lot more complicated, but we just want to know what's the equivalent resistance to this whole thing. Like if I want to be able to figure out the current in this thing, then I'm going to need to know what the resistances are in different places, right? Because I can't do that Ohm's law, V equals IR. I could do that here, but I'm not sure, in here, but like what's going to happen to the voltages in these, who's going to get 9 volts, who's going to get part of the 9 volts, right? It gets more complicated as we do those. So you really start to understand circuits when we start doing this. So what I'm going to do is I'm going to combine anything I combine, and I'm going to redraw this multiple times, right? So first thing I can combine here are these 2 that are in series. And if I have 2 resistors in series, the equivalent resistor to that is when I add them up. So if I've got a 2 ohm and a 3 ohm, that would be the same as going through a 5 ohm resistor here. And then this guy we left alone. So this would give me the same currents and the same voltages as this does. So that's why we call this an equivalent resistor, right? Now I'm going to add these two together when I add and make those into one equivalent resistor, right? So that's why we call it equivalent resistor. I tend to sometimes say like total voltage, and I really should say, or total resistance, and I should say equivalent. So we add 1 over 1, which is 1, plus 1 over 1/5, 1 over 5. So we've got a total of 1.2, and then I take the inverse of 1.2, and this would be a 0.833 ohm resistor is what we would need to be an equivalent resistor. So now we could say, well, what's the current, the total current? I wouldn't know the current here, right? Because the current's going to split. So off of this one, I couldn't know the individual amperages, but I could know the total current, right? We're going to come back and do that tomorrow. We'll build them back up tomorrow. Today, we're just going to bring them down and say, what's my total current? So we'll do V equals IR. So V over R equals I then. So 9 volts over 0.833 ohms. So 9 divided by 0.833 gives us 10.8 amps would be my total current, right? So some of that current would go here and some of that current would go here. We'll deal with that tomorrow. Let's look at another one. It's a little bit more complicated. Oh, that's got a whole bunch of things, right? To make math easy, we just went ahead and made all of them 2 ohm resistors. And we'll go ahead and make this guy 9 volts again. And we just want to make the equivalent resistor, figure out what my total current is. Again, the current would split here and it would split again here. We've got a couple of things going on there. So the first one I'll redraw, I can combine 2 things. I can combine these 2 and I can combine these 2. So I'll redraw this as 1 resistor. I can't combine this one with this one yet because, you know, those aren't the same yet. Let's right. So this is one pathway. This is one pathway. There are 3 different pathways here. So I'm going to have to combine some parallel things before I can go here, right? So this would still be the 2 ohm resistor. This one is now this, right? Let's do those as colors. We'll go ahead and do that as purple. And so that's 4 ohms right there. I'm going to leave off the unit so you can see that easier. Then I can do these 2 together in green. So now I'm going to come down here, come up and do green. That's also a 4 ohm resistor now. Let's see, I've got black. So I'll leave that guy I can't mess with yet. So I'll do that in black as a 2 ohm resistor. And then it comes up here, right? So this is the first one I can do. I was able to combine both those series ones here and both these series ones here. Now, the thing I can combine is all 3 of these are in parallel. Now, it looks like just these 2 are in parallel, but that's because I just drew this kind of weird here, right? Sometimes they get drawn a little bit different and stuff, but these are all, right? There's a Y split and a Y split right here. So this wire is a little different than that wire and stuff, but as far as this resistor, and this resistor, those are all 3 in parallel, right? So I could just draw that as 1 equivalent resistor there and 1 equivalent resistor there, with those 3 being this one. So we'll do that in green. So we're going to take a fourth, and a half, right? A fourth, and a half is going to be 1. So the equivalent resistor to this is 1, because 1 over 1, right? So we did, let's write that out. 1/4 plus 1/4 plus 1/2 equals 1 over Req, 1 over the equivalent resistor. So that's 1 equals 1 over Req. So we inverse 1, and that's still 1, right? So 1 is our equivalent resistor there. And then this guy is 2. So now my one last equivalent resistor is just those 2 added up. And that would be 3. So this is 9 volts. So my total current, remember, not the current here, or the current here, or the current here, or the current here, but the current here and the current here, right, where we haven't split, our total current would be 9 volts over 3 ohms. So it would be 3 amps would be our total current for this guy, right? Let's see. Let's do one more. That way you're a little bit more ready for the worksheet tomorrow. All right, one last one. Might be overkill for this part of it. We'll jump in tomorrow to build them back up, and I think that's kind of where they start to get to be more fun. and deal with switches and all that kind of stuff, right? Remember, if I've got a switch in here, what's the current right now? Well, 0. We don't have any current because the switch is open and it can't go through there. I could, on the other hand, build a short. This doesn't happen as much on paper, but on when we're actually building stuff, students will build shorts accidentally all the time. Well, what would a short look like? Well, if I set up my switch like this, if I close that switch, imagine what the electrons have to do that are going through there. The electrons go here and never do any job at all. Well, why would any electrons go this way, right? It's a path of least resistance. So if you're building something and then you were to close a switch and everything turns off at that point, well, your current's actually going to be really high now, but it's going this direction, not that direction. It's a bypass kind of thing, right? So you made a short. And if you short something, right, then it's not going to do any job. So we look at this one. What's the first ones we're going to combine here? It would be these three. So I'm going to go ahead and redraw this in a straight line. So I'll go, here's my 1 ohm resistor. There's that one. Now the equivalent to these three, we'll go ahead and make green. And then and then this one we'll make black. We didn't mess with either of those, so they're going to just stay the same. You should be able to do that one, right? Maybe pause me and do that one real quick. I don't even see my calculator, and I don't want to do that in my head right now. So we go 1/2 plus 1/3 plus 1/4, inverse that, right? Because it's the inverse of adding up the inverses, and you get 0.932 as the equivalent resistor. For that one, whoops, I was supposed to make that one in green, whatever. So then we'll draw a new equivalent resistor that's just going to be those three added together. Now I just add those up. So that plus 6, I'm not sure why I'm touching my calculator for a second there. 6.932 ohms is the equivalent resistance to this thing, right? So pretty simple to break those down. Tomorrow's worksheet, you'll start by breaking them down, and then you kind of have to build them back up step by step. So we'll do a couple of those together. And then you'll get some chances to work on some of those things on your own. So, today is pretty short. So, might not be a bad idea to go ahead and jump ahead to tomorrow's and start trying to work on those, because tomorrow's worksheet's a little longer. There's a few more examples for it and that kind of stuff.